terms one by one. Now this is the amplitude squared. Now this is actually the dynamics, that is the interaction of the particles are included here, and this is evaluated from Feynman diagrams using Feynman rules. So this is the part which is associated with Feynman diagrams. I will draw some diagram now every now and then, but we will not really evaluate m square in any case. That itself will take one lecture. Now this is the energy momentum conserving delta function. It simply says that the total force momentum in the final state, if I consider the scattering, this goes to n particles, then this is the energy momentum conservation. This delta 4 means there are 3 momentum conserving delta function and 1 energy conserving delta function. And this is the most important one for our purpose. This is the so-called phase space factor. Now this is an integral over the 3 momentum. This d3 tells you that this is an integral over px, py, pz. Now dqp is a volume element in the momentum space, and this 2 pi, actually this 2 pi h cross, I do not write the h cross here because we are using natural units. Now roughly speaking, a factor v times dqpi is the volume in the phase space. That is how many momentum configuration you can have if the momentum is having a particular value. Or in other words, if you look upon this dqpi as dpx, dpy, dpz, then the particle has a momentum p between p and p plus dx. Similarly, py is between py and py plus dy. So if this factor is large, then it simply means that there are many possible final states. Pi, remember, is a momentum in the final state. Therefore, this is a probability kind of factor. Actually, this comes from statistical mechanics. That this gives you the probability from dynamics. This gives you the probability of kinematics. That is, what are the values of the final state momenta subject to energy momentum conservation. Now this is very nice, but okay, let me write the formula for the decay also. I write dqpf there is a product over f, and then this is the energy momentum conserving delta function, and again a matrix element square, which again depends on dynamics. So we have a similar phase space here. Here it is assumed that the initial particle, let us say some A, goes to 1, 2, 3. There are F particles in the final state.
That will also be Ej.
Sorry?
The first equation Ej.
Oh yeah, sure. Thank you. Alright. So that is not the point, because we are not going to do this calculation at all. do I write all this? Well, for one reason. That is, let us count the independent variables for each of these processes. Now, here we have three particles. This is the initial state is known. We always take, if two particles are colliding, we always take that the initial energies and momenta we know. Either it's a fixed target configuration or a yes.
D sigma has the unit of Fermi square say, and whether dimensions are
And
also-
this is GV square.
okay.
This is GV square.
1 by G.
Or GV to the minus 2.
So on the right hand side there should be something that 1 by G square.
But don't worry too much about that.
Or it is contained in M square.
Yeah, M square has dimensions, for example. So we don't know that. So don't worry too much about that. The main thing is the counting. Now suppose I consider a scattering process or decay process, does not matter, a two particle final state. In technical terms we call it a two body phase space. Now here we have two such integrals then. Each is three-dimensional, right? So in general I have 6 variables of integration. Okay? Px, Py, Pz of one particle if you like, Px, Py, Pz of the other particle if you like. So 6. But they cannot be arbitrary. They must satisfy energy momentum conservation. And how many conservation relations are there? X component of the momentum must be conserved, Y component of the momentum must be conserved, Z component of the momentum must be conserved. Therefore, you can write this as 6 minus 4 equal to, that is, out of this 6 integration variable there are 2 independent. Out of this 2 you can take as theta and phi. For example, if you use spherical polar coordinates, you can take as theta and phi. Out of which for a 2 by 2 process the azimuthal angle dependence is trivial. Why? Because let us look everything into the center of mass. Change a variable cannot change by, in the center of mass what happens? These 2 particles are back to back. Therefore these 2 particles will also be back to back. Right? So it is basically 2 lines, the direction of the momentum. So we can assume that this is taking place on a particular plane. Right? This is called the scattering plane. And there is no harm in taking this to be the z-axis and this to be the x-axis. It is not necessary. But in this case, we see that phi is a constant on this plane. Because phi is actually dependent on the xz plane, the definition of phi. If you rotate it a little bit, a constant value of phi will be added, but nothing more. Therefore, the phi integration is trivial. Therefore, it actually has this is what we call azimuthal symmetry. This gives you 2 minus 1. Now this you all know, those of you who have done 2 by 2 scattering, you know that magnitude of momentum of the final state is determined by the energy of the initial state. Only the angle of scattering is unknown in this case, theta, and that is the independent. So what will be the, this should be remembered. And what is the so much in scattering because hardly we do 2 going to n scattering, although it can be done. This is mostly for decay, a particle decaying into a n-body final state. And then the corresponding formula should be for a n-body phase space, it should be n-body phase space, it should be 3n minus 4. Now of course azimuthal angle is not fixed. Why? Because suppose these 2 particles are produced, if one of them decay into 3 particles, let us say, it is not necessary that those particles will be restricted on the xz plane, and phi dependence can come because of that. So now this formula is quite general for a n-body phase space. In particular, 3-body phase space will have 5 integration variables. That is, you have to integrate 5 times, and the kinematics will give you the limits for this integrals. But for that we have to do individual processes. Alright. So this result I will preserve here for a 2-body phase space. Phase space, PS stands for phase space. There is one variable of integration, and for a 3-body phase space there are 5 variables of integration. Now let me come to the Feynman diagram business. Now let us consider first of all the W production diagram. Well, as I told you, in a hadron collider the W is produced by a QQ bar annihilation, let us say, and this wavy line is the W. So when we calculate, we have to calculate the matrix element square using the standard Feynman rules, and then what will be the phase space? It's a 1-body phase space because 2 initial particles going into a single final state. What about W decay? Well, W can decay, for example, into QQ bar. So decay in this channel will have exactly the same Feynman diagram. Although in this case, here I had a 1-body phase space. And here I have a 2-body phase space. Or if you wish, since I do E nu, it doesn't matter really, but let me write it in nu, and because this is the thing I will be calculating. W decaying into an electron and a neutrino. So it is clear that the matrix element of these two will be related, although the phase space integration will be different in the 2 cases. Therefore, they will be related, although their numerical factors will be different, because one has a 2-body phase space, the other has a 1-body phase space. Also, I have erased the formula. For example, in the cross-section formula, there was a 1/n for S in the denominator, there was a 1 over 2E in the denominator, where E is the energy of the decaying particle, of the decay formula. There was the 1 over 2E, which is the energy of the decay. So, having said all that, let me tell you that for this process, cross-section of W production will be those of you who have done beta decay or something, you know that this is the Fermi constant. What is S? This is the center of mass energy of the two quarks. So this is simply energy conserving delta function. That is, the energy of these two quarks should be equal to the mass of the W. That is simply giving you energy conservation, and these are coming from the matrix element phase space, etc. And for the partial width, we write gamma of W going to E mu. It is W minus, it will be minus E mu bar, and you will see that these are into a factor of 3. So you see that there are similarities in this formula, but here there is no remnant of the phase space, simply because of the fact that W mass is so big that you can do completely the phase space integration. Electron and neutrino have negligible mass, so you can do completely the phase space integration without having a constraint like the first one. The first one says that this process is possible only if Bhubaneswar is equal to F. So it's all very nice. I think I will preserve these two. But now let me go to the main business. That is Q2 bar annihilates into a W and then it decays into. But the question is, can I take this as a product of cross-section times branching ratio? It is tempting because in the beginning I was always writing like that. That the production of a particle, but this is an approximation, a very good approximation. And this is what I want to show. In order to convince you without any mathematics, I can give you a physical argument that when you have a Feynman diagram like that, you cannot always say that it is a cross-section times branching ratio. Let us consider this process.